everyone. Welcome. Welcome to today's talk on distributed deep learning with Anima Anandkumar. But before we start, I just want to give a little bit of an introduction to ABI.Seattle. My name is Sheila Oh. I'm one of the community leaders at ABI.Seattle. ABI.Seattle and ABI.Local is actually a local community that supports women in technology within the Puget Sound area. We're under the umbrella of the Anita Borg Institute, which you may or may not have heard of, is the host of the Grace Hopper Celebration, the annual conference that this past year had 16,000 attendees in Houston. So within the Anita Borg Institute, there's a lot of different programs. One of those programs is a community program. There is a listserv called Sisters, which some of you may be subscribed to. Other than that, there are different affinity groups that are part of the communities. And then we have the ABI.Locals that are currently within 20 different cities around the world, including Seattle, as well as New York and Chicago, Delhi, London, Tokyo, so all over the world. So our main goal is really to kind of inspire women to pursue and remain in technical fields and provide the guidance and the support they need to advance their careers. So our plans for 2017, this happens to actually be part of one of our tracks. We've decided to focus our programming this year on 3 different tracks: education, career, and community. And this is actually our first event within this education track. And we have been gracefully hosted by Amazon, and we want to give a special thanks to Amazon e-commerce services, who are in the back here, and they were the ones that provided the food as well as the drinks and hosted. So thank you guys so much. If you want more information about opportunities, feel free to talk with them, and they have a table in the back. And with that, a couple of things I just wanted to mention. Sorry. Okay. So just a reminder to silence your phones. If you want to tweet about the event, feel free to do so. And with that, I will hand the mic over to Laura Gritt, who's going to introduce the speaker.
Thank you. My name is Laura Gritt, and I am on the leadership team for Amazon Women in Engineering, and I want to welcome all of you here to the first event that we're doing here. And I have the privilege of introducing Anima. So she is currently a principal scientist in Amazon Web Services at Amazon. And her research interests are in the areas of large-scale machine learning, non-convex optimization, and high-dimensional statistics. In particular, she's been spearheading development and analysis of tensor algorithms. She has been the recipient of several awards, such as the Alfred P. Sloan Fellowship, Microsoft Faculty Fellowship, Google Research Award, among others. And she received her bachelor's in tech in electrical engineering from IIT Madras in 2004. She then received her PhD from Cornell University in 2009. After being a postdoc researcher at MIT, she then became an assistant professor at UC Irvine, where she was from 2010 to 2016. And she also was a visiting researcher at Microsoft Research in New England from 2012 to 2014. So I am very excited to welcome you and to learn more about deep learning.
Thank you. Laura and Sheila, and it's really great to see so much of community gathering late in the evening, and I'm very excited for the Anita Borg Seattle chapter. I'm in the Bay Area, but I'm here often visiting the team here. Half the team is here, so I'm here all the time, and I'm happy to get to know more of you when I'm here. So today I'll give an overview of, like everybody here has probably heard of deep learning, right? But what deep learning is about, what are some of the problems we've been able to solve, and also what are the challenges in having to deploy this on a large scale, and how in our team at AWS we are building many solutions to make this easier and to do this at a large scale. Yeah, so these are exciting times to be working on artificial intelligence and machine learning. We have access to enormous data sets, right? The primary driver of how we've been able to make so much progress is the availability of very large amounts of data. Whether you think about images, text, speech, biological data, right? We have access to more and more of data. And so this gives us an opportunity to learn more complex models from data. The other important component of this TRINITY is this class of algorithms. There is deep learning, there are various machine learning frameworks, how we can bring all this together under an umbrella to be able to process these large data sets. Right? So the third component perhaps that's often overlooked or not thought about is computing. So what's made this revolution possible is the availability of enormous compute power. So what earlier was only available in a supercomputer, which was only accessible, to a very small set of researchers, now anybody can go and access such compute power. And AWS is, enabling a lot of that in that space. So this third component also needs to nicely interact with the other ones, right? So meaning we enable seamless large-scale deployment of these deep learning algorithms, as well as be able to process large data sets quickly. And so all these three components are critical in further enhancing our progress in artificial intelligence. And I'll touch upon all these three during the talk. So as I said here, there are more and more areas now that are being revolutionized by deep learning. So it started with image understanding. There is the very popular MXNet competition where deep learning was able to improve performance by a huge amount, right? And when I say image understanding, it can be simple tasks such as identifying what are the objects in the image to more complex ones such as describing what the image is about. And then we have speech recognition, that powers Alexa, that powers many other speech recognition tools on how we can recognize human voices automatically. And in the space of natural language processing, again, there's a whole plethora of problems. Whether it's identifying sentiments, did this review, was it positive or negative? Whether it's translation automatically from one language to the other, right? So whether it is a combination of image and text, such as in captioning. So all these tasks, the more we can automate them and the more we can make it seamless, right, we'll be able to process large amounts of data. Because most of the data is going to be in the form of unstructured text, and how we can automatically process that is a huge challenge. And another area which has seen enormous growth is autonomy, in the space of self-driving cars or drones. Like all these settings involves now an additional component where there is control. So meaning as we are learning more about the environment, we have to make decisions and act on the basis of that. And there are real costs involved, right? There are risks involved in taking these decisions, especially if you have this car going, in a freeway. So the thing is, how do we do all this together and do this in real time? And that's where some of the most challenging problems lie. And here I've just shown a trend graph of how deep learning has really taken off over the years and has become a commonly used term now. So these are just some example applications on what we mean by image understanding. Right? The most basic version is where we are understanding what are the objects in the image and what we can detect. So if, for instance, in this example here, it's a beach, it's outdoors, there's a palm tree, right? It's landscape. So all these different attributes about this image, you can write this down. And the algorithm would also probably have different levels of confidence, right? So you're more sure that it's a beach, but whether it's a hotel or not, right, is much lower confidence. And so this is the basic task of object and scene recognition. So you can also do this for special class of images such as faces. So you may want to identify the person in this image, and you may want to verify whose face it is. In addition, you may want to do attributes that are specific to this image class, such as what the emotion is, whether there is the person has a beard, so that's specific to the face, right? So this way, then you can go more fine-grained within this category of facial analysis. And you can similarly do this, say, in terms of cars. You may want to go and look at a specific model of the car. So you can make it fine-grained within the broad categories that you have. And you may also want to do this in real time. In this example here, now there is this, oops, let me see. So there is the drone that is tracking the person in real time and able to, even as there is movement, able to keep the person in the frame, right? So, and this will be very challenging because you can see that when the drone is moving, there's going to be a lot of shakes, and it's going to be challenging to keep track of it. So there can be more challenging versions of object recognition. So you can also think of doing this to create new art, right? So this a nifty example is where you take images and you're able to transfer the style from your favorite artist and create new images. And this is learned automatically by the deep learning system because it's able to recognize what the features to maintain in the original image are and what the features are to be transferred from this stylized painting. And so these are just some examples on what you can do with a deep learning computer vision setting. And the framework behind it is this notion of a multi-layer convolutional neural network. So the idea is once you start with this raw image, it goes through several layers of processing where each layer has one set of building block units called activations, and then you process them layer after layer. And in the end, what you get is the confidence of the object being in each of the class, right? So with 85% confidence, it's a dog. With only 2% confidence, it's a cat. So you get this, and then you can threshold based on what these probabilities are to get a decision on what the object is present in this image. And the main intuition is the convolution operation lets you exploit the spatial information in the image, like how objects could be present in different parts of the image, still you should be able to recognize it as the same object, right? And that's what the convolution enables you. And the intuition is because you have these multiple layers, you get a hierarchical representation of your objects. The intuition is, you start with the layers at the bottom, that is the ones closest to the raw pixels. They will be made up of simple filters, and the more you go on the higher layers, they compose together into more complex shapes. For instance, in this picture, what you can see is these are the layer 1 activations, and as you go to higher layer activations, you can see that more complex shapes are activated here. So in layer 1, there are simple just lines, right? But by the time you go to higher layers, those simple shapes compose themselves to activate more complex objects in images. And that's the intuition that this helps you able to now detect that it's, as you go through these higher layers, that what is a dog, what does it mean to be a clock here, right? Various different objects. And so it's this multiple layers that make it possible to get the detection. Because if you just looked at the first layer, it's just these lines and very simple shapes. They don't form to be the actual objects in the image. But because of more layers, you get the compositionality effect. And that's the main intuition with any deep learning system, that the depth is what enables you to recognize complex shapes in images. So you can also take deep learning into the realm of natural language processing or any sequence-to-sequence models. So now I've just represented it as this a network that feeds to itself, meaning you have an input and then you have an output, but there is a state that can continuously feed to itself and progress in time. So the intuition now is you have memory, right? Because you start somewhere, in the input sequence, and then you keep iterating over the states. I think it's clearer if I now unroll it, meaning there is a start point, and this is the input sequence, and this is the output sequence. And now you can see here these intermediate layers maintain a state. So they maintain latent state representation that changes over time. As you move further in the sequence, you're also updating the state. And the example task I've shown here is you want to predict what is the next character in your model here. So if it's, so you're feeding in B, you want to get E if the word is beer, right? Because you want to predict the next character that will come up. And there will be certainly some probability that it can be these different characters. And the intuition is once you have BEE, right, there are only few possibilities of what the last one is. And this can you directly learn from data is the question. That's a simple example of a character level model. So you can do this model at different levels. You can do this at the word level where you feed in a whole sentence. Right? This is actually at the sentence level. So you feed in a whole sentence and you want an output to be the expected response of it. So if you ask this model, how are you, it should be able to tell that one of the valid answers is I'm fine. Right? So can you learn such patterns of input and output given a whole lot of training data? And that's what these sequence models can accomplish, which is sequence-to-sequence learning. So both the input and the output can be now a variable-led sequence. And how can we train this for various tasks? So once you have this, naturally you can train it now to have responses for various questions, right? So different kinds of question and answering. You can have it for translation, where the input is the source language, the output is the target language. So you can have now a variety of tasks that involve language that can incorporate these sequence models. And this is now another class of deep learning models. So I'll first introduce some of the recent services our AWS AI team has launched that has these deep learning components built into that. And then I'll introduce also the framework of MXNet, which is the deep learning engine that powers, and it's the deep learning of choice for AWS. So so there is Rekognition, which does image analysis, as I just introduced. There is Lex, which will work on natural language and speech data. And Poly is the service where you converge text into speech. And I will briefly introduce what each of these do. So the idea of Rekognition is to enable deep learning to process large amounts of image data to understand objects, to understand the scene. And as I said, there is a separate component that will enable also to do face analysis and facial detection. Right? So one part of it is to be able to describe the scene with varying conferences. So if you input any image into Rekognition, you can come up with categories with their various confidences. And with faces, you can recognize different attributes such as emotion. There is the different attributes of the face. And the idea is facial recognition will be important for a number of systems, so you can use recognition to be able to do verification, search, and similarity between the faces. And that's the idea so this is a new service. I encourage you to try this out. The idea is through deep learning, we can now process large amounts of images very effectively. And this is built with the AWS infrastructure, so it's seamlessly integrated with other services at AWS. So now let me just briefly tell you what Lex does. So the idea is, if you think about the evolution of how we are interacting with machines, right? There is the first generation where we had to learn how to talk to the machine. So we had to go learn different programming languages, whether it's C, C++, or before that it was even, like assembly level code or whatever the level was, we had to learn that to interact with the machine. And then it got better, and then we have now interfaces to interact with the machine, right? So there are now nice user interfaces that lets me input with, like could be the smartphone, could be different UIs that are designed well. So now the next framework is intent-based, meaning the machine knows what you would like without you having to tell everything. Right? So the machine is personalized for you. The machine is able to understand what you require from it. And building this is the next wave. And this is where now we want chatbots or conversational agents that can seamlessly do this. And Lex is a service that lets you launch such chatbots in a very easy and seamless manner. So the idea is you can do both voice and text chatbots, and it's powered by Alexa if you use the voice interface, and it's also there is integration with Facebook Messenger, Slack, and many other services. And just to give a very brief idea of how you can go about doing this, right? So the goal is, suppose a user says that book a flight to London. Right? There are so many different parts that need to be processed. First, you need to do speech recognition. Right? So you need to figure out what words were uttered. But then after that, you need to link them to a knowledge graph to figure out that London means the airport at London, and it's most likely London Heathrow. And flight means it's booking a flight, and that's a specific function. Right? And then you can look at, there'll be so many of other missing information. So what we figure out is what's the origin and destination, but then when is the person departing, is this a round trip, right? So there is so much new information that will be needed, and then that's what the algorithm has to figure on what to ask next. And suppose you ask about the departure date, you can get new information and you can complete the loop again. And that's the idea that this is an interactive system where it's continuously asking the user for new input, and at the same time updating the fields to figure out what decision to make next. And Lex lets you build such chatbots very quickly. And more details you can find on the web. I will not spend time on this. So Poly is another deep learning based service that will let you convert text to speech. Right? So if you want automated conversion, this is usually challenging. So let me just demonstrate.
Tired of sitting by her sister on the bank and of having nothing to do. Once or twice she had peeped into the book her sister was reading, but it had no pictures or conversations in it. And what is the use of a book thought Alice, without pictures or conversations.
So this was one of the samples. So there are several challenges if you think about being able to do this processing accurately. For instance, you want this
Today in Seattle, Washington, it's 11 degrees Fahrenheit.
So, you want this to be automated.
We
You
live
want
for the
it,
music live from the Madison Square Garden.
so you want this to be also intelligible and
How
easy
much
to
wood would a woodchuck chuck if a woodchuck could chuck wood?
right? So you want it to be able to do all the tongue twisters very effectively. And this is actually quite important. You want to figure out what the semantic meaning is. So the humans will immediately figure out that if it's a number and it's somebody person's, then it's a phone number.
Richard's number is 2,122,341,237.
Right? So that's not the answer you would like.
Richard's number is 212-234-1237.
So the idea is Poly lets you, embed these semantic meanings into the text, so you can figure out how to translate it into voice for different scenarios. I mean, humans are very context-based on how they, translate text to voice, right? And incorporating that into an automated system is challenging. And the other is to be able to have customized pronunciations,
My daughter's name is Kaja.
which is probably not the right
My
one.
daughter's name is Kaya.
Right, so you would like to have all this in a system when it comes to automated text-to-speech, that it should be accurate, but it should also have contextual information and change the way it outputs the voice depending on what the semantic meaning is. And it should be able to do a lot of tongue twisters pretty seamlessly. And also give the user the ability to customize pronunciations. And the idea is it's based on deep learning. It's at the same time built for production, so you can quickly launch this and be able to convert large amounts of text into voice. So now that I've showed you some services which enable you to use AI, let me now go into MXNet, which is the deep learning engine, and the framework of what's gone behind it. Right? So the idea is now if we have to run these large-scale deep learning applications, how do we go about building a package that can that is efficient and that is easy to program and that can make it easy to debug as well. And MXNet is an open source package that started with efforts at various universities, and now at AWS in our team, we are also actively developing and contributing to this Apache open source framework of MXNet. So what I've shown here, don't worry about the detailed picture, but the idea is this is a pretty complex network. Right? This is the ResNet. It's one of the ImageNet competition-winning networks here. So if you were to code this from scratch, this is impossible because it's a lot of connections. It's billions of parameters. So this is not something you can do bookkeeping from scratch. So you need nice frameworks that can enable this. Right, so that's one aspect that if you want to deploy this in practice, it's complex to code. The other is it requires a huge amount of computation. So even just processing a single image could take billions of flops, right, and floating point operations. And the idea is the GPU will give you a better compute power compared to CPU, but there are other issues involved with GPUs. How do I enable this on these different hardware architectures is something we need to worry about. And the other is also memory consumption, because as you keep adding more layers, you have more parameters. How do you keep track, and how do you compute such large number of parameters is something you need to worry about. So when it comes to the main things to look for in a good deep learning package, one of the important ones is programmability. So as we have more and more complex deep learning architectures, whether it be with convolutional networks or with sequence models, right, we need to be able to quickly and easily program these network definitions, as well as more complex, say, training mechanisms which go beyond gradient descent. So that's one aspect. Can we think of have a package where programming is easy? The other is portability. So now we are at a juncture where we want to run deep learning on a variety of different platforms, and ideally you don't want to be writing code again and again. So can you write the code once and be able to use it across a variety of different hardware, and which also can adapt to a variety of different uses of memory. So if you're running this on a smartphone with very limited memory, can you easily adapt your existing code to handle that? And the last one, the important one, is efficiency. So there are two parts. One is during training, the other is during inference. So training means that you're using the data to update your network. Right? So you're trying to figure out what is the right set of parameters for this network. So inference is when you're scoring, meaning you take an image, you're detecting what are the possible objects in the image. And during both these scenarios, you want to have high efficiency. And especially if we are deploying this on the cloud and the customers are paying for the cloud time, this becomes even more important. And as we make the networks larger, as we invest more in the compute power, this is going to be even more important. Right? So these are the things to look for if you want to select what's an appropriate deep learning package. And today we have a variety of choices. I talked about MXNet. Of course, there are a number of other packages that have both different pros and cons. So what I'll show you today is how MXNet is able to address a number of important issues in the space of this programmability, portability, and efficiency. And that's the reason why we say that AWS is declaring MXNet as the framework of choice, and we are now contributing actively to this Apache open source project. And that's the idea, and also there is seamless integration with AWS that we'll see. So let's first address the programmability issue. So I've listed a variety of different languages. I'll just take a short poll on what's your favorite language or what's your most comfortable language. So for how many of you is C++ among the choices here? Okay, not many. Python? Yeah. That's expected. Scala? No one. It's not a Scala community. R? Yeah. So R is also, I think, usually a very unaddressed market, right, when it comes to large-scale learning. Julia? Usually there's one or two, but it's more exotic. And then there is, Go, and there is others, so I don't know if I'll continue with the poll. But the idea, sorry?
Oh, and MATLAB.
Yes, MATLAB. Probably, no one wants to admit even if they so the idea is, there are a variety of different languages. They have pros and cons, and depending on your background, you're comfortable with one or the other. Right? So what the MXNet philosophy is, the front end is independent of the back end. So irrespective of what front end language you use, there is a single back end that connects to highly optimized libraries, both on GPU and CPU. Right? So, and now any updates that happen on the back end will, still separate it from the front end. And so this is the way now to then scale up, because, if you're an R user, you're happy and comfortable with doing this, yet you want a very large-scale system, now you can enable that with MXNet. And Also, this philosophy separates, thinking about writing a single machine implementation to this much more complex, distributed, large-scale implementation. Because at the back end, you can have very efficient libraries that are optimized for that specific architecture, right? Whereas in the front end, you're separated from all those gory details. And so this is a nice modular framework as well. And the other is the programming paradigm itself, right? So the simple Python code here, it's an imperative framework because you go line by line and you manipulate it. And the idea is these are usually these are much simpler to write. This is how the human mind thinks in a sequential way, right? So these is the program will be simple and easy to debug. But this is very challenging if you think about optimizing, especially for parallel programs, right? Because you don't have the full computational picture beforehand. So these are not good for optimization. Right? The other framework is the declarative framework where you first declare all the variables and what the computations are before the actual computation happens. So that means here you can come up with this computation graph, and this way now you can do different optimizations. For instance, you can figure out that this is an intermediate computation. You don't need a separate storage allocated for that, right? You can overwrite it after it's done. So this part is, once you have the computation graph, you can apply complex optimization frameworks for both compute and memory optimizations. But on the flip side, usually this is less flexible. This requires much longer programs that you need to write. It's harder to read and debug. And so the thing is, instead of picking one versus the other, why not do both? And that's what MXNet does. It lets you do both imperative and declarative programming. So the idea is there may be some parts of the program where you don't need to optimize, right? You can just directly write out these equations and then it's easy enough to work with them. And there may be other parts where it's important to optimize and then you can write the declarative one. So in this example here, in the declarative part, there is also, you can now incorporate the imperative part, aspects into it. And you can also do the opposite where you can embed symbolic expressions into imperative programming. So in this example here, if you're doing a gradient update in your deep learning, it's very convenient to write it as an imperative program. But then you may want to load network architectures that may be defined in a symbolic manner. So you can mix both of them here. And so depending on your framework, depending on where you care about optimizing for memory and compute, you can use declarative programming. And in other parts, you can use imperative programming. And this mix lets you, come up with much shorter, easy to read programs, and at the same time get good efficiency. So this lets you decide what's the right balance rather than fixing on one paradigm. Yeah, so that was about programmability, that how with a choice of different front-end languages, with a choice of both declarative and imperative programming, now we are giving programmers a lot more flexibility and to define different architectures. So the next one is programmability. So what MXNet allows you to do is be able to fit all the core library, all the dependencies into a single source file. So this way now you can compile it on any platform that you'd like.
Frying pan, lemon, frying pan, espresso, espresso, espresso. Orange, 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 banana, banana.
So this was on a smartphone, so in real time there is object detection, and that was done using MXNet on JavaScript. So it's very quick to be able to deploy such an application on your smartphone, any IoT device, and so you don't have to write a program from scratch to be able to do that. Yeah, so now let's address the performance issue, right? So if, as I said, if you're running this on a large scale, you would like to ask, as I keep increasing, say, the number of GPUs or number of instances, how does the efficiency change? So ideally, you would like your efficiency to grow linearly as you add more compute power. But in practice, there's always overheads, right? There's overheads of how there's communication between different GPUs, how much does the control layer take up, and so on. And of course, if you think about how to parallelize programs, that is always a tricky, complicated one. So here, this even if you just had 2 GPUs and the CPU here, and if you want to figure out where to send the different operations, right? There is the forward pass and there is the backward pass in the network. It gets hairy and complex if you try to do this for every operation, which is what would happen if you use like an MPI framework. This is just not possible, right? So you can't go and hand code every possible operation that occurs on various GPUs and ask how they should coordinate with one another. So that's why classical frameworks such as MPI is not suited when you have to now run this on a large scale and when you have to have mostly an automated framework on how to optimize as you add more and more devices. So the philosophy of MXNet is to do a hierarchical parameter server. So the idea is here at the lowest level are the workers. So in the case of deep learning, they are GPUs because GPUs is where we get the best efficiency. And the idea is there are now servers at different levels that will take updates from the workers and then push the the combined result back into the servers, right? So in this level 1 server could be one of the GPUs themselves. And now with just communication among the GPUs, in a high-speed network, right, this can be very fast. So most of the time you're just communicating within the GPUs without going to the CPU. And once in a while you will go up to the CPU, and that's the level 2 server only when needed. So the idea is to try to keep the operations as local as possible and to use high-speed communication whenever needed and to only go up the stack when and as required. And with this now framework, you can get very good efficiency. So I'll show you some numbers on how we are able to scale across multiple cores in the same GPU and also across multiple GPUs. And these are the P2 instances, which are GPU instances on AWS. And we also have these benchmarks available on GitHub, so anyone else is also welcome to go try them out. And so you can see that in this case here, so these are 16 GPUs on the same machine, and the ideal is this linear curve, the red one, and we are very close to it, so it's 91% efficiency. So you can get very good efficiency by communicating a lot within the GPUs and only going to CPU as needed. And MXNet is highly optimized to do such operations. And the Inception and the ResNet are the state-of-art networks. The AlexNet is the older one, so the performance in terms of accuracy is also better in these newer ones. And you can see it can also be made more efficient. And now you can also look for optimizing across multiple instances, right? So in total, these are 256 number of GPUs, so that means 16 different instances where each instance consists of 16 GPUs. And again, you can see that there is some drop in efficiency, but very minimal. So you get up to 88% efficiency even when you scale up across the instances.
Excuse me, could you repeat how you measure efficiency?
So the efficiency here is like how much the throughput, like how many images you can process per second. Once you go, these are the networks that are fixed, right? So for this network architecture. Any other questions? And so the idea is, and there are more details, in the benchmark website that I mentioned. So this is giving a bit more details that this was on the ImageNet set of images, and the ResNet also has some more kind of details of which one it incorporated. Yeah. So so far we saw that MXNet is nice properties of being easily programmable, it's portable, and it's also highly efficient when scaled up across multiple GPUs as well as multiple instances. So now we'll see how we've also integrated it seamlessly with the AWS infrastructure that will allow you to do what I call like one-click or a few-click deep learning. And the idea is AWS offers all the end-to-end, right? Starting from these P2 instances, which are high-powered GPU instances, to these armies, which are pre-configured to do deep learning, and you can now build these deep templates to have clusters of deep learning systems. So just to give you some back-of-the-envelope calculations of the compute power that these GPU instances offer. So if you take a P2 16 extra large instance, that's 16 K80 GPUs, and that's about 70 teraflops, right? And the experiments that I showed you had 16 such instances. That's about 1.1 petaflop. So just to compare it with the world's most powerful supercomputer, that's 93 petaflop. So you can get very close to the most powerful supercomputer with just a click of few buttons. And this is what the cloud way levels the ground, because it makes it possible for anybody to access these large amounts of compute power. And we are also moving even more and more in terms of having better hardware on AWS. And so the other aspect is these mission images or armies. These are pre-configured for deep learning. So usually if you have to set up a cluster in your cloud, or you have to download a whole number of libraries, you have to set up all the dependencies, that's usually a big pain. Right? So what these mission images enable you to do is everything is pre-configured, so you don't have to download or install anything from scratch. So this is just a very quick demo. I mean, it's kind of sped up, but just to show you how with a very few clicks you can get this going. So you can start in the console, the AWS console, and you can create a stack. And this is where you can load existing templates that will enable you to get the process started quickly. And you can select which instance type you would like. It's a P2 instance. And then you provide SSH location, how many workers you need. You can name your stack. This I had initially created for NIPS, so that's what the name stays. And so these are all the details of loading various keys, setting up. But just I want you to get the sense that this is just a few clicks, and you can have the stack of the deep learning going. And so there you've created the stack, and you can now monitor and see what the various ones are. So you can go to the EC2 management console, right? And then you can see all the instances, and you can see what the status is for them. And you see that now you have the workers that are up. So now to train, you can now load your training script. So that's what we are doing here. We are launching the jobs from a GitHub repository of MXNet. And and that's it. Now you have the training going. So basically it's now started training. And this was on MNIST, but you can do it on any data set. And you can always monitor and then ask, So that's the idea, right? So again, don't worry about all the details, but as you saw, with just a few clicks, you can get the deep learning going by selecting what kind of instances you like, and the deep learning army is already loaded with various features. And so in terms of the roadmap of where we want to go from here, with respect to the MXNet development is, since it started as a university project, there's still a lot more we can do in terms of having more comprehensive documentation and tutorials, and that's where we also want it to be a community effort and get more people trying out MXNet, talking about their experiences. I encourage you to go also try out the Deep Learning Army on AWS and let us know the feedback of how easy it is to learn this and try this out. And the other aspect is at the same time we are pushing towards asking what are new machine learning algorithms we can do, right? Can we speed up training of deep learning? Can we come up with better algorithms? Can we incorporate more sophisticated data types into our framework? So my earlier research at UCI involved looking into tensors, which are extensions of matrices. So how can we enable that at large scale? These are some of the things we've been working in the group. And at the same time, we have a number of engagements in terms of community outreach. And if you are working on research, there are AWS credits available. I forgot to mention there's also the AWS Educate program. If you're teaching classes and you would like AWS credits for you and your students to work either in machine learning or on other computer science projects, that's available too. And we always have a number of positions open in our group. Thank you.